So we have today Ph.D. Physics qualifying exam practice problem number 3 in classical mechanics. So consider the following: h equals p sub x squared plus p sub y squared over 2m plus m omega squared over 2 times the quantity x squared plus y squared plus lambda xy. For part A, we want to write Hamilton's equations. Okay, so Hamiltonian mechanics and normal modes problem here. So Hamilton's equations are q sub I dot equals partial of h with respect to that p sub I, and then p sub I dot equals that negative partial derivative h with respect to q sub I. And for x, x dot equals a partial h with respect to p sub x equals p sub x over m. And for y, this y dot equals that partial h with respect to p sub y, and that's going to equal p sub y over m. So for p sub x dot, that equals that negative partial h with respect to x equals negative the sum of m omega squared x and lambda y. So p sub x dot equals negative m omega squared x minus lambda y. And for p sub y dot, that's equal to negative partial h with respect to y. That equals negative this quantity, this sum of m omega squared y and lambda x. So p sub y dot equals negative m omega squared y minus lambda x. X dot equals p sub x over m, y dot is p sub y over m, and p sub x dot equals negative m omega squared x minus lambda y, and p sub y dot equals negative m omega squared y minus lambda x. Equivalently, x double dot plus omega squared x plus lambda over m y equals 0, and y double dot plus omega squared y plus lambda over m x equals 0. Okay, so moving along to part B. Part B, determine all equilibrium points. So just going to switch now to part B, see if this holds. I don't think it will. Oh, it did. Oh, temporarily. Let's see. Okay, so for part B, equilibrium points. So the equilibrium point in phase space satisfies the following: x dot equals y dot equals p sub x dot equals p sub y dot equals 0. And from here, x dot equals p sub x over m equals 0. Y dot equals p sub y over m equals 0. And we obtain p sub x equals 0, p sub y equals 0. Okay. The momentum equations require negative m omega squared x minus lambda y equals 0 and negative m omega squared y minus lambda x equals 0. Equivalently, m omega squared x plus lambda y equals 0 and lambda x plus m omega squared y equals 0. So if we put this in matrix form over here, for our first row here we have m omega squared lambda, second row lambda m omega squared, and then we have this column xy's that equal to 0, 0 column. Determinant of the coefficient matrix is delta equals the quantity of m omega squared minus lambda squared. And if lambda does not equal 0, then the only solution is x equals 0, y equals 0. So we could say, thus, for generic lambda, satisfying lambda squared does not equal m squared omega to the fourth. The unique equilibrium point is x comma y comma p sub x comma p sub y, which is just 0, 0, 0, 0. The exceptional cases are worth noting. If lambda equals m omega squared, then the coordinate equations become x plus y is 0. So there's a flat direction along that line, y equals negative x. And if lambda equals negative m omega squared, then the coordinate equations become x minus y equals 0, or x equals y. So there's a flat direction along y equals x. for the stable oscillator case, which will be found below, to require magnitude or absolute value lambda is less than m omega squared, then the unique equilibrium is the origin. Okay, part C. So for part C, going back here, linearized equations around the equilibrium. So for part C, just going back, we want to linearize the equations of motion around the equilibrium for part C. Sorry about that. So starting with this, whoops. Okay, so linearized equations around the equilibrium. So the Hamiltonian is exactly quadratic, so Hamilton's equations are exactly linear. Therefore, the linearization about the equilibrium point is identical to the exact equations. And about the origin, x, y, p sub x, p sub y equals 0, 0, 0, 0. And the first order system is this: x dot equals p sub x over m, y dot equals p sub y over m, p sub x dot equals negative m omega squared x minus lambda y, and p sub y dot equals negative lambda x minus m omega squared y. So what we could do from here, we define the phase vector, the z equals, that's x, y, sorry about that, that's a y, x, y, p sub x, p sub y for this column. Okay, and for this, the linearized system can be written as z equals az, where a equals this matrix. Entries for the first row, 0, 0, 1 over m, 0. Entries for the second row, 0, 0, 0, 1 over m. Third row, negative m omega squared, negative lambda, and then, sorry about that, 0, 0. And for the fourth row, negative lambda, negative m omega squared, 0, 0. Okay, and equivalently in the second order form, x double dot plus omega squared x plus lambda over m y equals 0, and y double dot plus omega squared y plus lambda over m x equals 0. Okay, so that's for letter C. And now going to letter E, we want to determine the normal mode frequencies. So the normal mode frequencies for here, let's see if this stays up. Okay, so normal mode frequencies. To find the normal modes, try the solutions of the form x of t equals x e to the I nu t, y of t equals capital Y e to the I nu t, where x and y are constants. Then x double dot equals negative nu x e to the I nu t. Okay, and from here, y double dot equals negative nu y e to the I nu t. Substitution into the second order equations gives that negative nu squared plus omega squared times x plus lambda over m y equals 0. And from here, that lambda over m x plus quantity negative nu squared plus omega squared times y equals 0. So we could set up this matrix here, this omega minus nu squared, lambda over m for the first row, lambda over m omega squared minus nu squared in the second row, and times this column x over y, setting it equal to 0. Now what happens here is a non-trivial normal mode requires the determinant to vanish. So we take the determinant of this piece here, set it equal to 0, and that omega squared minus nu squared quantity squared, that quantity squared minus lambda over m squared equals 0, and omega squared minus nu squared equals plus or minus lambda over m. So this gives the two squared normal mode frequencies, that nu, so plus squared equals omega squared plus lambda over m, and that nu minus squared equals omega squared minus lambda over m. And taking this positive square roots of these, the nu plus equals square root of omega squared plus lambda over m, and that nu minus equals square root of omega squared minus lambda over m. identify the corresponding eigenvectors next. So for the mode with x equals y, the two coordinates move in phase y equals x, substituting capital Y equals capital X into quantity omega squared minus nu squared times x plus lambda over m times y equals 0. That's going to give us omega squared minus nu squared plus lambda over m equals 0. And nu squared is going to equal omega squared plus lambda over m. So x equals y, say nu plus squared equals omega squared plus lambda over y. And for the mode x equals negative y, the two coordinates move out of phase. Y equals negative x, substituting y equals negative x. Okay, what we now have is the following. We have that omega squared minus nu squared minus lambda over m equals 0. So nu squared equals omega squared minus lambda over m, and x equals negative y. And we get nu minus squared equals omega squared minus lambda over m. For part E, we want to determine the stability condition. So just going here, for part E, find the condition on lambda for stability. So stability condition here. Whoops. Might as well change these. Sorry about that. Make it a little easier, hopefully. Hopefully this will hold up. Sorry about that. Okay, so here we go for the stability condition. For the stable bounded oscillatory motion, both squared frequencies must be positive. Therefore, that V plus equals omega squared plus lambda over m is greater than 0, and V minus squared equals lambda is equal to omega squared minus lambda over m is greater than 0. So the first inequality implies that lambda is greater than negative m omega squared. Second inequality implies that lambda is less than m omega squared. Combining these two gives negative m omega squared is less than lambda is less than m omega squared. Okay, equivalently, see what we have here. Absolute value lambda is less than m omega squared, and if absolute value of lambda equals m omega squared, then one of the normal frequencies has to be 0. Okay, now from here, this means that the potential has a flat direction, so the equilibrium is marginal rather than stable. And if the absolute value of lambda is greater than m omega squared, one of the squared frequencies is negative. Corresponding normal coordinate grows or decays exponentially rather than oscillating, so the equilibrium is unstable. This conclusion can also be obtained from the potential energy quadratic form. V of xy equals m omega squared over 2 times the quantity x squared plus y squared plus lambda xy. And the matrix of the quadratic form is given here. And the matrix is positive, definite exactly when m omega squared is greater than 0, and when the quantity m omega squared minus lambda squared is greater than 0, which would give absolute value of lambda is less than m omega squared. Okay, and for part F, we want to determine these canonical transformation and diagonalization. So for letter F here, construct a canonical transformation that diagonalizes the Hamiltonian. The canonical transformation and diagonalization of the Hamiltonian here. The coupling term lambda xy suggests rotating to coordinates along the directions x equals y and x equals negative y. So we're going to define q sub 1 equals x plus y over square root of 2, and q sub 2 equals x minus y over the square root of 2. Now, coming from here, so we get the corresponding momenta should transform should transform in the same orthogonal way. Piece of 1 plus piece of y over square root of 2. Piece of 2, piece of x minus piece of y over square root of 2. So the inverse transformation is x equals x of 1 plus x of 2 over 2. Y equals q sub 1 minus q sub 2 over the square root of 2. Sorry, that's a q sub 2. And piece of x equals piece of 1 plus piece of 2 over the square root of 2. Piece of y equals the difference between piece of 1 and piece of 2 over square root of 2. Now the verification that the transformation is canonical, the original non-zero fundamental Poisson brackets are here that x piece of x equals 1 and y piece of y equals 1, and all other fundamental Poisson brackets vanish. If we compute this q sub 1 piece of 1, we get that for the brackets inside x plus y over square root of 2, piece of x plus piece of y over the square root of 2. That's going to become 1/2 times this entire thing. X piece of x plus x piece of y plus y piece of x plus y piece of y, and that's going to yield 1/2 times 1 plus 0 plus 0 plus 1, and that's just 1. Computing the q sub 2 p sub 2, that equals x minus y over the square root of 2, piece of x minus piece of y over the square root of 2. So we have 1/2 times this whole thing, x piece of x minus x piece of y minus y piece of x plus y piece of y, and then we get 1/2 times the quantity 1 minus 0 plus 1, and that also equals 1. So the mixed brackets vanish. Q sub 1 p sub 2, that's x plus y over square root of 2, p sub x minus p sub y over the square root of 2. And then we wind up getting here that 1/2 times the quantity 1 minus 0 plus 0 minus 1, and that equals 0. And then moving forward here, for q sub 2, q sub 2 p sub 1, that's x minus y over square root of 2, p sub x plus p sub y over square root of 2. We're just going to perform these operations. We're going to get the 0. So 1/2 times 1 plus 0 minus 1, that's 0. And then q sub 1, q sub 2 equals 0. P sub 1, P sub 2 equals 0. Therefore, the transformation preserves the canonical Poisson bracket structure, that Q sub I, P sub j, that equals the Kronecker delta. And then this is going to be equal to 0. And P sub I, P sub j equals 0. So the transformation is canonical. Rewriting the Hamiltonian for the kinetic term, that p sub x squared plus p sub y squared, that's equal to quantity p sub 1 plus p sub 2 over square root of 2 squared, plus this whole thing, p sub 1 minus p sub 2 over the square root of 2 squared. Okay, and now that becomes 1/2 times the quantity p sub 1 squared plus 2 p sub 1 p sub 2 plus p sub 2 squared, plus 1/2 times quantity p sub 1 squared minus 2 p sub 1 p sub 2 plus p sub 2 squared, which yields the following here: the p sub 1 squared plus p sub 2 squared. P sub x squared plus p sub y squared over 2m is p sub 1 squared plus p sub 2 squared over 2m. And x squared plus y squared equals the quantity x sub 1 plus x sub 2 over square root of 2 squared, plus x sub 1, x sub 2 over the square root of 2 squared. This is going to be now 1/2 times the quantity x sub 1 squared plus 2 x sub 1, x sub 2 plus x sub 2 squared. And then that's going to be 1/2 times the quantity x sub 2, 1, and minus 2 x sub 1, x sub 2 plus x sub 2. That's squared. So that x sub 1 squared plus x sub 2 squared. Some people call this x sub 1, 2, x sub 2, 2. I'm just going through, by the way, I'm going through this fast. If I mispronounce anything or miscommunicate because my brain hasn't had coffee today, please forgive me. The math, though, and the steps are correct. But if I miscommunicate anything with the variables, please forgive me. I tend to do that sometimes because my mind is, I don't know, it wanders. Okay, so moving along from here, last page. So we're going to get, for this, for our m omega squared over 2 times the quantity x squared plus y squared, that equals this. And the coupling term lambda xy equals this. And we're going to substitute into the Hamiltonian here. So h equals the following. And just cleaning this up a bit, the diagonalized Hamiltonian equals this. Okay, so the rest is kind of just organizing everything and making the Hamiltonian look nice. Okay, so there's our Hamiltonian, and now we have, if we define our new plus squared equals omega squared plus lambda over m, our new minus squared equals omega squared minus lambda over m. And so our Hamiltonian can be this. So this is the Hamiltonian of two independent harmonic oscillators. So the canonical transformation has fully diagonalized the system. All right, and now just moving along here, general solution in time. Let me just get this out of the way here, sorry. And then just adding on to this, if we wanted the general solution in time for the stable case, absolute value of lambda less than m omega squared, the normal coordinate equations are this q sub 1 double dot plus nu plus squared q sub 1 equals 0 and q sub 2 double dot plus nu squared minus q sub 2 equals 0. And here are equations for q sub 1 of t is a sub 1 cosine here, and for q sub 2 of t, a sub 2, this whole cosine, and then b sub 2 sine of that mu, nu minus t. So returning to the original coordinates, we're going to get the following here. X of t equals q sub 1 t plus q sub 2 t over root square root of 2, and y of t equals q sub 1 of t minus q sub 2 of t over the square root of 2. So the constants are fixed by the initial conditions. Okay, sorry if I miscommunicated anything, but the math and the setups are correct, thankfully. Thank you very much for watching, and have a great day.